Okay, I'm glad to see that the number of people that's evaporated is not very large during this 5-minute break. To answer the question that was asked before, I think one of the problems with the models is, first of all, with respect to feedback, it's cloud cover. The problem is that because you cannot resolve very small scales, the cloud cover physics is basically parameterized with a recipe, and because it's parameterized with a recipe, whichever recipe you decide to use, whatever you cook depends on the recipe that you use. So that's one thing. Another problem is that the models are incorrect because they don't include all the radiative forcing or all the physics that the models should include. Anyway, I'm going to talk about results on, or relatively new results on the solar climate link. We've seen a lot of evidence, even today, that the sun has a large effect on climate, but if you want to use it or to enter it into models, you need to know how large is it, not only that it is important qualitatively, but also quantitatively, how large is this radiative forcing. So this is what I'm going to talk about today. Okay, so how strong is this radiative forcing, and why is it important, for example, to understand climate change? So I'm going to begin with trying to elucidate why knowing the radiative forcing is important. Then I'll go ahead describing you how you can use the oceans as a big calorimeter to measure this radiative forcing, and then talk about implications. Okay, why is knowing the radiative forcing important? First of all, it's interesting because you want to explain the climate. You want to understand what's driving it. But with respect to global warming, it's interesting because if you look at the 20th century warming, you see that there was some type of warming over the 20th century, if it's 0.6 or 0.7 or who knows what. You want to explain it with some kind of radiative forcing. Of course, some natural fluctuations can be important as well, but I'm not going to talk about them. You know that there is a given change in temperature, and you want to know what is the radiative forcing because the radiative forcing times the sensitivity of the climate, namely how the climate behaves following changes in the radiative forcing. This thing is going to translate into a given temperature. So if you try to explain 20th century temperature increase with a small radiative forcing, you will necessarily need a model with large sensitivity. Okay? If, on the other hand, the sun is important over the 20th century, for example, it means that the total radiative forcing over the 20th century is going to be larger. If you have a larger radiative forcing, then the same given change in temperature should be explained with a lower climate sensitivity. Okay? So, and basically climate sensitivity is the trillion-dollar question because if we know what the climate sensitivity is, it will tell us how much, for example, the temperature is going to increase because of us humans, for example, over the 21st century, etc. Okay? So, the biggest question is, what is this radiative forcing of the sun? Okay, this is an example. This is one of the nicest examples I know of the fact that the sun affects the climate. It's a qualitative result which shows you that the sun is affecting the climate. What you see here are, on one hand, you see a proxy for solar activity. It's in fact a proxy for cosmic rays, which we now know is probably the thing that drives climate. And that's the carbon-14 that you get out of tree rings. Carbon-14 is formed by spallation from cosmic rays which hit the atmosphere, but these are modulated by the sun. So the upper graph that you see over there is solar activity. The bottom graph, that's oxygen 18 to oxygen 16 isotope ratio from stalagmites in a cave in Oman. And this is sensitive. What?
What's the time? Is there a time scale on
Yes, there is a time scale. Since the group is German, they put a dot instead of a comma over there. Okay? That's thousands of years. It's a group by Augusto Mangini in Heidelberg. There are other very nice results, but this is one which is particularly nice. So you see that there's a big correlation between solar activity and climate, and the question is it driven, for example, by changes through total solar irradiance and a super high sensitivity, or is it driven by some other mechanism? So you want to quantify the effect somehow. Okay, so what we want to do is to use the oceans. Why do we want to use the oceans? Because over a short time scale of, say, 11 years, the Earth doesn't have time to heat up or cool because of its very large thermal inertia. Most of Earth is, of course, oceans. Arthur C. Clarke pointed out quite interestingly quite a few years ago, that we shouldn't have been calling it planet Earth, we should call it planet ocean, because most of it is an ocean. Anyway, because of this large volume of oceans, over the 11-year solar cycle, any changes in the radiative forcing don't translate, or almost don't translate at all, to changes in the temperature. Basically, all the heat is absorbed and then re-emitted from the oceans. So if we calculate the amount of heat that there is in the oceans, or the change in the amount of heat in sync with the 11-year solar cycle, we can, in principle, see what is this solar forcing. Okay, so we use the oceans as a calorimeter, and over this time scale, you see that most of the heat content, or most of the change in the heat content in Earth is indeed due to the oceans, and all the other components of the climate system are minute. So basically, it is a very good calorimeter. Okay. So how can we measure the amount of heat that there is in the oceans, that goes into and out of the oceans? Well, there are several data sets that we can use. We can use, for example, the ocean heat contents that you have from buoys that were basically from the geophysical year, from 1955. There's a lot of data collection across the oceans, and that's basically a four-dimensional data set. It covers the oceans, like the three-dimensional volume of the oceans, and time. You can, in principle, use the sea surface temperature as well, but the sea surface temperature is not a direct, doesn't tell you directly what is the heat content. For that, you need some modeling of the diffusion of the heat into the oceans. And another very good type of data set, that's the sea level change rate. And the reason is that over short time scales, most of the change in the volume of the oceans is simply thermal expansions. So if the oceans absorb heat, they simply expand, and you see it in a form of rising sea level. Each of these data sets has different pros and cons, and they are a compromise between quality of the signal and systematic errors which might hide or lurk somewhere in them. Okay, one of the data sets is, of course, what I said, tidal gauges. This is an example of a record from San Francisco, which goes all the way back to the middle of the 19th century. The good thing about tidal gauges is that they cover a long time scale. Basically, from the 1920s onwards, you have a good coverage around the world. It gives you very good statistics. One of the reasons is that, in principle, you need a good measurement in one location in order to get the behavior of a whole oceanic basin, because over this time scale of 11 years, the sea level equilibrates, okay? You cannot have the waters of the southern Atlantic 1 meter higher than the waters in the northern Atlantic, because the water will flow. Okay, so basically, the sea level is a good averager, which gives us average data, as opposed, for example, to the heat content, where we need to measure it in all the different locations in order to get good data. However, we may be suffering from systematic errors, because over this time scale, you start getting other contributions, such as glacial melt or freezing. Okay. If you look at the sea level variations, this is an estimate for the contribution of thermal expansion versus other components, and you see that it is the major component, but it is not, the other components are not negligible. So you have to take it into account and to correct it and hope that the correction is okay when you're doing it. On the opposite end is the heat content in the oceans, and Here you're measuring directly the heat content in the ocean, so it's basically, it's not supposed to suffer from systematics in the sense that there's other signals which are entering your measurement. However, the coverage is bad, especially if you go back in time, or if you go future in time. It turns out that the coverage used to be better than it is today. And you see that you don't cover the world oceans properly. However, as I said, it's a good direct measurement. Okay, so what, okay, this is, for example, the total heat content that you get, and there are basically two groups that do that. And what you see here is that the heat content in the oceans changed. There's a slow increase trend, but over that there are a lot of variations. And we're looking at these small variations of something which is, has to do with the 11-year solar cycle. Okay, so what do you get? What you see here, this is for the past 50 years. At the top you see the heat, at the top you see the cosmic ray flux or the solar irradiance. Basically they change together, so you see all these solar cycles. Do I have a pointer? I'll point with this. It's okay. Here, it's okay, I have a high-tech thing.
Oh, okay.
My cursor.
Oh.
Here you see solar activity. Here you see the flux which goes into the oceans based on the ocean heat content, which has a large error because of the completeness. But you do see that there is a correlation in the sense that every time there was a solar maximum, there was also more heat going into the oceans. Here, this is the change in the rate of change of the ocean sea level. And again, you see that whenever there was a solar maximum, the sea expanded because it was absorbing heat. Now, mind you, people who usually look at the sea level change rate, they corrupt the data in the sense that it's not very useful in order to measure this thing. The thing is that if you want to measure the sea level change rate, because the tidal gauges are not continuous in many places, there are a lot of segments, you first have to differentiate the data and then add it, as opposed to add it and then differentiate it, because every time you add or subtract a tide gauge record, you're going to ruin your data. So you have to keep, you have to do the order correctly. Anyway, but once you do it, you see that the ocean expands every time that the sun has a solar maximum. At the bottom, you see here changes in the sea surface temperature, which are noisy, but they do correlate as well. This is the sea level change rates going all the way back 100 years, but from about the 1920s, when you have a good enough data set, you see that basically the oceans expand and shrink, or contract every time, or in sync, totally in sync with the solar activity, okay? You see both graphs vary together. You see the correlation? Even they see it. Okay. Okay, so you can take these data sets, these variations which you see in sync. You can look at what you can take the component of each variable which varies in sync with the solar activity, and then translate it into changes in the or a flux which goes into and out of the ocean, and this is what you get. You find that here, this is let's look at the lower graph. If you look at the three different data sets, whether it's directly the ocean heat content, the surface temperature, or the tidal gauges, you find that they are all consistent with a value, this value, which is about 1.3 plus or minus 0.4 watts per square meter every solar cycle. For comparison, the variations of the total solar irradiance in radiative forcing over the solar cycle is 0.2 watts per square meter. So it means that the amount of heat which is going into the ocean every solar cycle is about somewhat less than 10 times more than just variations in the total solar irradiance. So that tells you that there must be some mechanism which does amplification, which amplifies solar activity. Okay, the oceans are absorbing almost 10 times more energy, 6, 7 times more energy than you would expect from just variations in the total solar irradiance. Strangely enough, or not, if you look at the changes in the cloud cover, which are in sync with variations in the solar activity, okay, this is a graph by Svensmark, you can translate these changes in cloud cover into changes in the radiative forcing using measurements of, say, the Earth radiation budget experiment. And what you find is that the total forcing that you would expect from cloud cover plus changes in the total solar irradiance is something like 1.3 plus or minus 0.3 degrees. So what you see which enters and leaves the ocean every solar cycle is exactly what you would expect within the error from cloud cover changes, which are in sync with solar activity or with cosmic ray flux. So it doesn't, this thing by itself doesn't tell you that the variation or the amplification mechanism is necessarily that of cosmic rays and cloud cover, but it tells you that such a mechanism must operate. And the only mechanism which can give you something which is that large, which is known at least, is that of cosmic rays and cloud cover. Okay, so we've seen the numbers. The question is, what does it imply to global warming? Take here the arrow bars with a grain of salt that are, I just added them in quadrature. So they don't have a lot of meaning because they're so large. But let's see, for example, suppose we want to explain what happens over the 20th century. Over the 20th century, if you open the IPCC report, and assuming you believe it, the anthropogenic forcing, namely everything except solar, is something like 1.2 plus or minus 1.5 watts per square meter, at least eyeballing their graphs, and that's roughly 2 sigma errors. If you believe the IPCC report, then the only solar forcing that you have over the 20th century is that of direct changes in the total solar irradiance, and that's about 0.2 watt per square meter, maybe 0.17 or whatever. This means that if you want to explain the 0.6 degrees increase in temperature, you need the sensitivity, which basically can be anything. Any sensitivity can be explained, and the reason is that you don't know the forcing. The error on the forcing, because of the indirect aerosol effect, is so large that you can explain everything you want with a large sensitivity. On the other hand, if solar forcing is not only because of the TSI, but it includes also an amplification mechanism, which we have proof which exists, it means that you need to explain this temperature increase with a solar forcing which is much larger than this one. Okay? You also get the added benefit that because solar forcing is not monotonic, it increased until the middle of the 20th century, then it decreased, and then it increased again. You explain the natural variability much more, you explain the variability much more naturally, and here I mean naturally, literally, by nature. And then if you try to ask yourself what is the radiative forcing that you need in order to explain this 0.6 degrees, then you have to take the sum of these numbers as your radiative forcing, and what you find is that the sensitivity of Earth climate to changes in the energy budget are somewhat close to a feedback-less Earth. Okay, Earth without any feedback would be 1.2 degree Celsius or Kelvin increase for doubling the amount of CO2. Okay, what does it imply to 21st century warming? If you take an unknown sensitivity, basically you can get any number for what the temperature increase is going to be over the 21st century. However, if you take a value which is consistent with the total forcing, one which includes a real solar effect, you would see that total temperature increase because of solar activity, because of human activity over the 21st century, assuming we will double the amount of CO2, and I don't think we're going to double it, because I'm optimistic that we're going to do other stuff before, the temperature increase is only going to be a small 1 degree. Okay, so just to summarize, okay, you can actually use other timescales as well to constrain the sensitivity, and you find that once you include Cosmic-ray flux variations on half a dozen different timescales, from geological to 20th century warming to 11-year solar cycle, you consistently get from all the different timescales a sensitivity between 1 and 2 degree, or 1 and 1.5 degrees Celsius for doubling the amount of CO2. Okay, so just to end, there's an amplification mechanism. It implies that a large fraction, at least half of the warming of the 20th century is because of the sun. It means that the sensitivity has to be on the low side, and it means that we don't have to worry about warming over the 21st century.